I want you to imagine just for a second that you apply for a mortgage. You go to the bank and the loan officer types your entire life into a computer.
Right. They put in literally everything.
Yeah, your income, your credit history, that one time you missed a credit card payment 5 years ago, your debt, everything you have ever worked for.
It is all just data points to them.
Exactly. And so 3 seconds later, after hitting submit, a big red denied flashes on the loan officer's screen, and you are just devastated.
Oh, absolutely crushing.
You ask the officer, you say, why? What was it? Was it that credit card I opened last year? Is my income just like slightly too low for this bracket?
And you expect a clear answer.
Right. But they just look at you completely helpless and they say, I don't know, the AI just said no.
Which is, it is the ultimate modern nightmare, isn't it? Being completely judged and, frankly, having your life altered by a machine that just refuses to explain itself.
It is terrifying. And, usually when we talk about a piece of modern technology, there is this underlying expectation of precision. Like if you look at traditional software engineering, a developer writes a script and they tell the program exactly what to do, literally line by line.
Yeah, it's very deterministic.
Right. So if there's a bug or if the program denies a mortgage when it obviously shouldn't have, the engineer just goes in, points at the code and says, there it is. On line 402, there is a broken if statement.
Right. Because traditional code is binary. It is explicit. It's essentially just a massive, complex chain of if A happens, then do B.
Broken or not broken, it's clean. And importantly, if I am the customer in that scenario, I can at least get an actual answer.
And that clarity is really comforting to us. Humans like things to be visible, to be categorized, and to be entirely within our control. We want to be able to lift the hood of the car and see exactly which belt snapped.
Yeah, exactly. But then you step into this world of machine learning and artificial intelligence, and suddenly that clean, transparent machinery is just, it's gone.
Poof, vanished.
The hood is practically welded shut. We are looking at a landscape that is incredibly murky. We are dealing with the ultimate black box problem here.
It is the absolute definition of diagnostic muddy waters. Because we are feeding these massive, frankly incomprehensible amounts of data into these neural networks,
right,
we aren't giving them explicit rules anymore.
Right, no more line 402.
Exactly. We're giving them examples, millions of them, and letting them figure out the rules on their own. And then they're outputting decisions that shape human lives. Who gets a loan, who gets a medical diagnosis, which products roll off a global assembly line.
And that right there is exactly what we are untangling today. In this deep dive, we are looking really closely at how professional engineers are legally, mathematically, and, ethically forced to explain the unexplainable.
Which is a tall order.
It really is. We are exploring the reality of how these enterprise systems are wrangled, secured, and kept from just going completely off the rails. And, whether you are a developer looking to upskill and build these systems or just someone trying to navigate a world that is increasingly run by them, understanding this framework is basically non-negotiable at this point.
It really is.
Yeah.
Because the magic of AI, it isn't just in building a predictive model that gets, super high accuracy in some pristine, sterile lab environment.
Yeah.
Honestly, anyone with a laptop can do that now.
Right. There are tutorials everywhere.
Yeah, the real magic, and honestly, the real existential challenge we face is the rigorous, sometimes incredibly messy reality of keeping that model safe, fair, and actually functional when it collides with the real world.
So based on the source material we are looking at today, which are guidelines for professional machine learning engineers, we are going to break this down into 4 massive pillars. These are the pillars engineers use to establish trust with these AI systems.
The foundational blocks.
Right. So first we have to start with explainability, which is actually peeking inside that black box. Then we have to figure out how to watch the AI over time, which is monitoring.
Crucial step, that one.
Oh, yeah. Third, we have to tackle the whole ethical minefield, which they call responsibility. And finally, we have to lock the whole thing down with identity and access management, or IAM.
It's a phenomenal architecture for governance, honestly. And it's so important to remember that these aren't just like abstract philosophical concepts we're discussing.
No, these are hard rules.
Exactly. If you're building a system at an enterprise scale, these are hard, practical engineering requirements. If you fail at literally any one of these 4 pillars, your entire AI initiative collapses.
Okay, so I want to jump straight into that first pillar then. Explainable AI, or XAI. How do we actually explain the unexplainable? The documentation out there for professional ML engineers lays out a really fascinating taxonomy for how this is done in the field.
Yeah, they break it down very cleanly.
Yeah, there seem to be two major divides. The first divide is intrinsic versus post-hoc explainability. What does that actually mean for an engineer on the ground?
Let's break those down because that distinction really dictates how you build your entire project from day one. So, intrinsic explainability refers to the nature of the model itself. Some mathematical models are just inherently understandable by design.
Like, they're just simple by nature.
Right. Think of a really simple linear regression or a basic decision tree. If you build a decision tree to approve loans, you can literally trace the branches with your finger on a screen. You say, okay, income over 50K, go left, credit score over 700, go right, boom, approved.
You can just read it.
Yes, you can look at the math and see the exact transparent logic path that it took to get there.
Okay, I like to think of this sort of like a restaurant.
Okay, I'm listening.
So intrinsic explainability is like going to a place where the kitchen is completely open. You know, you are sitting right at the chef's counter. You are watching them cook the meal step by step.
Oh, I like that.
Yeah, you see them add exactly 1 teaspoon of salt. You see them sear the steak for exactly 3 minutes. When the plate is finally put in front of you, you know exactly what went into it and exactly how it was made.
That is a perfect analogy. You watch the entire process happen. But here is the huge problem in modern machine learning. Those simple open kitchen models, they often just do not have the predictive horsepower necessary for highly complex tasks.
Right, they're too simple.
Exactly. A basic decision tree is great for a super simple personal loan, but it absolutely cannot process human language. And it definitely cannot recognize, like, a tiny tumor in a high-resolution MRI scan. For those complex tasks, you need deep neural networks or massive ensemble models.
And those, I assume, are the closed kitchens?
Those are the closed kitchens. You place your order, the swinging doors shut tight, you hear a lot of chaotic banging and fire and yelling inside, and 5 minutes later, this incredibly complex, mysterious, but frankly delicious dish comes out.
But you have no idea how they made it.
None. You know the output is good, but the process is a total mystery. And that is where post-hoc explanations come in.
With post-hoc meaning after the fact.
Yes, exactly. We have to take the finished, fully trained model, the black box, and essentially reverse engineer the recipe to figure out what the heck it was thinking.
It's like eating the finished dish and trying to guess the spices by just tasting it over and over again. Okay, so that is intrinsic versus post-hoc. But there is a second divide that seems just as important in the material, which is global versus local explainability.
This one is all about the scope of your explanation. Global explainability means you are trying to understand the entire model's behavior across, like, all possible inputs.
The big picture.
Right. If we look at every single prediction this model has ever made, what features generally matter the most? Does a person's income matter more than their age? Does their zip code matter more than their credit history? It's the 10,000-foot view of the model's brain.
Got it. So local explainability, on the other hand, is about zooming all the way in on one specific individual prediction.
Yes. Why did the model make this exact decision for this exact person on this exact day?
So going back to my restaurant thing, local is me reviewing the specific plate of spaghetti that just arrived at my table and asking the waiter why it's way too salty. But global is like a food critic reviewing the entire restaurant's menu and cooking philosophy over the course of a whole year.
Yeah, and what's fascinating here is why this distinction between local and global matters so deeply in a real business context. Because you need both, but you need them for entirely different audiences.
Who needs what?
Well, you might need global explanations for government regulators. If you're a major bank, federal regulators are absolutely going to knock on your door and demand to know, just generally, how your credit risk model operates.
Right, to ensure it's structurally sound and not systematically biased against a whole group of people.
Right, the government wants to see the whole menu.
Huh.
But a global explanation is completely, totally useless to a customer who is standing right there at the teller's desk asking, why was my specific mortgage application denied?
Yeah, the teller can't just say, well, generally speaking, our model cares most about income.
Exactly. The customer is going to say, I make plenty of money. Why did you deny me? They need a local explanation. They need to know if it was their specific debt-to-income ratio or maybe their specific late payment from 3 years ago that triggered the denial today.
Okay, I am totally with you on the taxonomy so far.
Mhm.
We have open kitchens and closed kitchens, and we have the whole menu versus the single plate of spaghetti. But how do we actually do it?
Ah, the engineering part?
Right. If I have a closed kitchen, a massive post-hoc black box model, how do I actually force it to give me a local explanation?
Well, this is where we get into the actual software tools. And the engineering ecosystem splits these tools into two distinct camps. You have model-specific methods and model-agnostic methods.
Let's start with model specific. What does that mean?
So model-specific tools only work on certain types of mathematical architectures. For example, there are tools out there like integrated gradients, XRAI, GradCam, or tree gain-based importance.
What a jargon.
A ton of jargon. But the point is, you can't just plug these into anything. GradCam, for instance, is specifically designed to reach into the internal layers of a convolutional neural network.
Which is a model used primarily for images, right?
Yes, exactly. It reaches in and pulls out the specific mathematical weights to see what the model is visually looking at. But if you try to take GradCam and use it on a text-based model, it will just fail. It completely breaks.
Right.
It requires that specific visual architecture.
It's like having a highly specialized diagnostic tool that only plugs into, like, a Honda Civic.
Perfect analogy.
If you try to plug it into a Ford, nothing happens. The port doesn't even fit.
Precisely. But then on the other side, you have the model-agnostic tools, things like Lime, permutation importance, and the absolute heavyweight in this entire space, which is called SHAP.
Okay, I have seen this term everywhere when people talk about explaining AI. SHAP. It stands for Shapley Additive Explanations, I think. Can we really dig into this? Because it seems like actual magic when you see it work, but I know it's just math. What is SAP actually doing under the hood?
It is brilliant, and it actually originates from cooperative game theory, which is wild, because it was invented long before modern AI even existed. A mathematician named Lloyd Shapley invented the core math in the 1950s.
The 50s. Okay, walk me through the game theory part.
Imagine you have a team of players who are playing a game together, and let's say they win a cash prize of, say, $100. You need to figure out exactly how much each individual player contributed to that win, so you can divide the $100 prize fairly among them.
Okay, so if player A scored literally all the points, they get all the money. If player B just sat on the bench eating snacks, they get nothing. That makes sense.
Exactly. But what if it's a highly cooperative game where the players interact constantly? Player A passed to player B, who blocked for player C. Shapley came up with a mathematical formula to calculate the exact fair numerical contribution of each player in that complex scenario.
Okay, I'm tracking, but how does this apply to machine learning?
Now fast forward to modern ML. SHAP takes that exact same game theory math from the 50s, but it changes the variables. The game is now the model's prediction. The players are now the features of your data, like age, income, and zip code.
Ah, I see.
And the prize, the $100, is the final output value of the model. Like, let's say, predicting a house price of $500,000.
So it's trying to figure out, like, how much the income player contributed to the $500,000 prize.
Yes, exactly. It generates individual prediction feature scores. It'll literally tell you, okay, for this specific local prediction, the baseline average house price in this area is $400,000. But the square footage feature pushed the value up by $150,000.
Okay.
The bad location feature pushed it down by $50,000, and the age of the house pushed it down by another $10,000. And the magic is, when you add all those individual feature scores together with the baseline, you get the exact final prediction.
That is incredibly elegant. And the beauty of this is that it gives you a flawless local explanation. Like, you know exactly what pushed the price up or down for that one specific house.
And crucially, if you take thousands of those local explanations and just average them out, you can aggregate them to form a global explanation of the model's overall behavior, especially on tabular data like spreadsheets or on text data.
So if you evaluate enough individual plates of food, eventually you reverse engineer the entire restaurant's menu.
Bingo.
It sounds perfect. I mean, it's highly interpretable, it's a really compact representation, and the math guarantees that all contributing features are considered. The prize is fully fairly distributed, but,
Right.
I mean, I'm guessing there is a catch. There's always a catch.
There's always a catch in engineering, yeah. SHAP is incredibly powerful, but it has three really significant drawbacks that engineers have to constantly wrestle with. The first is that it ignores feature interactions.
Let me stop you right there. What does that actually mean in practice? Because if it's looking at all the features to divide the prize, how is it ignoring their interactions?
It goes down to how the additive math works. It evaluates each feature's contribution as an average of its impact across all different combinations, sure, but it forces the final output to be a simple sum, plus this, minus that. But in the real world, features don't just add together cleanly. They multiply, they cancel each other out, they interact super deeply.
Can you give me a real-world example of that?
Definitely.
Yeah.
Let's take a medical model predicting the risk of a heart attack. Two of your features in the dataset are high fever and age. Right.
Up?
Having a high fever might mean one thing if you are 20 years old. Maybe it's just the flu, so it's a very low risk of a heart attack.
Right, you just sleep it off.
But having that exact same high fever means something completely different and far more dangerous if you're 90 years old. The interaction between the age player and the fever player is literally the most important part of the diagnosis.
Ah, they multiply each other's risk.
Yes. But SAP, by forcing everything into individual additive scores, it can really struggle to fully isolate and explain that complex nonlinear interaction. It might just assign a generic positive risk score to fever and a positive risk score to age, totally missing the nuance that they amplify each other exponentially when combined.
That makes a lot of sense. The players aren't just scoring points independently on the court, they are passing the ball to each other, and SAP kind of misses the pass.
Exactly.
Okay, what is the second drawback?
The second one is weird. It can create new data points that may be completely unrepresentative of reality.
Wait, what? How is an explanation tool creating data? It's supposed to just read it.
Think about how you would theoretically calculate a Shapley value. To figure out how important the income feature is, you essentially have to ask the model, hey, what would your prediction be if we just didn't know the applicant's income?
Okay.
But a machine learning model isn't built to handle missing data. It expects a number for income. If you just leave it blank, the code literally crashes.
Oh, right. It needs a matrix of numbers. So how does SHA get around that?
It simulates the missing data, it masks the real income, and substitutes it with like an average income from the background data set, or sometimes just a random value, just to see what the model does when that feature is scrambled.
Okay.
This means it is forcing the model to make predictions on synthetic hypothetical data points.
Ah. And the problem is, those hypothetical data points might be physically impossible in the real world.
Exactly. Let's go back to real estate. SHAP might mask the number of bedrooms feature to see how important it is, and it substitutes an average value from the whole city. So now it's asking the model to predict the price of a 500 square foot studio apartment that somehow has 4 bedrooms.
Oh, wow. Yeah, that physically cannot exist.
Right. That data point cannot exist in the real world. So the model's prediction on that impossible data point is going to be wildly erratic. And SHAP is using that erratic prediction to calculate its final explanation, which means it provides an approximate accuracy, not a perfect bulletproof one.
Okay, so it ignores interactions, and it forces the model to sometimes hallucinate impossible scenarios. What is the final con?
The final con is just pure, brutal mathematics. The computational cost is astronomically high on large feature sets.
Why is it so high?
Because to find the true, exact Shapley value, mathematically, you technically have to evaluate every single possible combination of features in the data set. Let's go back to the game theory again.
Okay.
If you have just 3 players, A, B, and C, there are only a few combinations to test. You test player A alone, A and B, A and C, A, B, and C. It's fast. If your model has 10 features, calculating every combination is still manageable for a modern computer. But what if your model is analyzing a spreadsheet with 1,000 columns?
Oh no, it's an exponential curve, isn't it?
It is the combinatorial explosion 2 to the power of 1,000.
It's a big number.
It is a number so incredibly large that if you harnessed every single computer on Earth right now, the universe would end before it finished calculating the true Shapley values for a single prediction.
Okay, so if the math is literally impossible on large data sets, how are engineers actually using this in the real world today? Because they obviously are. Let's ground this in a scenario.
Yeah, let's look at a classic tabular data scenario. Compliance at a major bank. Let's say you are an engineer at this bank. You are tasked with developing a new credit risk model to approve or deny business loans. And to get the absolute highest accuracy, you decide to use a deep neural network built in TensorFlow.
And let's quickly define TensorFlow for anyone who hasn't used it. It's basically this massive open source software library developed by Google, specifically designed for building and training complex neural networks. It's like the heavy machinery of AI.
Exactly. You bring in the heavy machinery. So you build this massive neural network. It's incredibly accurate. But because you are a bank, you operate under really strict federal regulations. The law mandates that you must be able to explain exactly why a loan was denied based on the applicant's features. You cannot use a black box.
So you have a major conflict here. You built a closed kitchen, but the government is actively demanding an open kitchen.
Right. And you want to use SHAP to explain it, to open the kitchen. But your TensorFlow model has hundreds of features. The combinatorial explosion means you simply can't compute the exact Shapley values before the sun burns out. So what is the engineering solution? The architecture outlined in professional deployments uses a tool called Vertex Explainable AI.
With Vertex AI being Google Cloud's fully managed machine learning platform.
Yes. And specifically, to solve this exact math problem, Vertex Explainable AI uses a method called sampled Shapley.
Sampled Shapley. So it's what? It's cutting corners?
Well, it's an approximation algorithm. Instead of calculating every single possible combination of features, which is impossible, it calculates a statistically significant random sample of those coalitions.
Okay, so it bounds the computation time.
Exactly. It allows you to get a highly accurate, regulatory compliant explanation showing exactly how much the income, credit score, and debt contributed to the denial without melting your cloud servers and completely bankrupting the IT department.
That is a brilliant compromise between mathematical purity and just operational reality. So that covers tabular data, spreadsheets, numbers. But I really want to contrast that with visual data. Because explaining a spreadsheet is one thing. Explaining how an AI looks at a photograph is entirely different.
It is a completely different paradigm, yeah. Let's look at a manufacturing scenario for this one.
Okay, set the scene.
You work for a massive manufacturing company. You are tasked with training a custom image classification model. There is a camera at the very end of an assembly line, and it takes pictures of metal gears as they roll past on the belt. Your model needs to look at the photo and classify the gear as either pass, it's good, or defective, throw it out.
So it's a classic computer vision problem.
Right. So you build the model, you train it, and overall, the metrics look great, 99% accuracy. But you have a holdout set.
And a holdout set, just for the listeners, is simply a batch of data, in this case, photos of gears, that you intentionally hid from the model during the training phase. It's the final exam. The model has never seen these photos before, so you use them to test how well it performs in the real world.
Perfect definition. So you run the final exam, and you notice a terrifying pattern in the results. Some images in your holdout set are being consistently mislabeled, and the model is doing it with incredibly high confidence.
Oh.
Yeah. The AI is 99% sure that a gear is perfectly fine, but when you look at the photo with your own human eyes, there's a massive, obvious crack right down the middle of the metal. It is visibly, dangerously defective.
So how does an engineer actually figure out what the model is looking at? I mean, SHEP can't help you here. There are no columns of data to evaluate. It's just millions of pixels.
This is where visual explainability tools become vital. If you are using Vertex AI, the specific solution for computer vision is a tool called XRAI. Yes, XRAI. It takes a completely different approach from SEP. It doesn't look at individual pixels one by one, because a single pixel, like one tiny red dot, has no meaning to a human. Instead, it segments the image into small, meaningful regions, which we often call superpixels. It groups pixels that share similar colors or textures together.
Okay, so it kind of blobs the image together. How do I use that to debug my blind AI?
When you configure the explanation request in the system, you set the visualization type to outlines, and you set the polarity parameter to positive.
What does that actually look like when the engineer opens the file on their computer? What do they physically see on their screen?
Imagine opening the photograph of that cracked metal gear on your monitor.
Yeah.
Now, if you just ran a normal prediction, the model output simply says prediction, defective, confidence, 99%.
Right, which tells you nothing about the why.
Exactly. You have no idea why it made that choice. But with XRAI configured with positive outlines, the system actually alters the photograph itself. It literally draws bright, glowing neon outlines around the specific superpixels in the image that most positively drove the model's decision.
Oh, that's cool. It's acting like a highlighter pen for the AI's brain.
Precisely. It highlights the evidence.
Oh.
And this is exactly how you catch catastrophic failures before they hit production. Because when the engineer looks at those glowing outlines, they might logically expect the outlines to be drawn right around the crack in the metal, right?
Yeah, that's what makes it defective.
But instead, they look at the screen, and they see the glowing outlines are drawn around a dark shadow cast by the factory lighting in the background of the photo.
Oh, wow. Not on the gear at all.
Yes. The engineer suddenly realizes, oh my God, the model isn't looking at the gear at all. Because in the training data, maybe all the photos of defective gears just happen to be taken on a Tuesday afternoon when the lighting cast a weird shadow on the belt.
The model is lazy.
Exactly. The model is incredibly lazy. It didn't learn what a crack looks like. It learned that a specific shadow correlates with a defective label. It just learned to find shadows.
And without a tool like XRAI physically highlighting the pixels, you would never, ever know that. You would just deploy a model that approves broken gears and rejects perfectly good ones, and you'd be completely blind to the reality of why it's failing.
Exactly. Explainability isn't just about government compliance.
Yeah.
It's about basic, fundamental, functional debugging.
Okay, so let's say we've done our jobs. We've used sampled Shapley for our spreadsheets. We've used XRAI for our images. We know exactly how the model thinks today. We fixed the shadow issue. We have our baseline of trust established, and we deploy the model into the real world. We're done, right? We can just go on vacation.
If you go on vacation right then, you will come back to a total disaster.
Why? I mean, if the math is right and the logic is verified, shouldn't it stay right? Traditional software doesn't just spontaneously forget how to do math while I'm on a beach.
And that right there is the fundamental paradigm shift from software engineering to machine learning engineering. Traditional software degrades because the internal mechanics break. A dependency library gets updated and breaks your code, or an operating system patches, or a server just runs out of memory.
Right, the code itself rots.
Right. But machine learning models don't degrade because the code rots. The code actually stays exactly the same forever. Machine learning models degrade because reality shifts around them. A model is nothing more than a frozen mathematical snapshot of the world as it existed at the exact specific moment the training data was collected.
But the world absolutely refuses to stay frozen.
Exactly. The world is incredibly dynamic. Consumer behavior changes, economies crash, global epidemics happen. And when the real world diverges from that frozen snapshot the model was trained on, the model's accuracy just plummets.
And that brings us beautifully to the second pillar, model monitoring. We have to set up alarms in the control room to tell us when reality has actually shifted. The engineering documentation outlines the inevitable decay of AI by defining two distinct phenomenons. You have skew and you have drift. I really want to clearly define these because they sound very similar, but they are fundamentally different alarms. Let's start with skew. Specifically, training serving skew.
Training serving skew happens when the data the model was trained on historically differs significantly from the data it is currently seeing in production today, which we call serving.
So the baseline for skew is the original training data itself, the old textbook.
Yes, exactly. You are comparing today's live real-time traffic against the historical textbook the model read months or even years ago. For example, imagine you trained a model to predict housing prices and used a massive data set of real estate transactions from, let's say, 2018.
A completely, totally different world.
Radically different. Interest rates were different. Inventory was different. Remote work wasn't a massive market-shifting factor. The mathematical relationships between a house's features and its actual price were highly specific to 2018. If you take that exact model and put it into production today in the current market, it's going to fail spectacularly.
Because the serving data, the current market conditions, has skewed completely away from the 2018 training baseline. The statistical distribution of the features is just mismatched.
Exactly.
Okay, so that's skew. It's comparing the present against the distant past. What about drift? Prediction drift.
Prediction drift is entirely focused on the present. It is comparing today against the very recent past. The baseline for drift detection is not the original training data. The baseline is the statistical distribution of the features seen in production just a few days or weeks ago.
So it's completely ignoring the 2018 textbook.
Yes. It's asking, is the traffic I am seeing right now fundamentally different from the traffic I saw last Tuesday? Imagine you have a massive e-commerce site. You have a model recommending products to users. Suddenly, over a tiny 48-hour period, the distribution of user clicks changes massively. Maybe a massive celebrity influencer endorsed a really obscure product on TikTok, or some weird viral trend started out of nowhere.
Right, so the inputs the model is receiving right now are drastically drifting away from what it considered normal just last week.
Exactly.
So to summarize it in my head, skew is the model screaming, this doesn't look like what I was taught in school. And drift is the model screaming, this doesn't look like what I saw yesterday.
That is a perfect way to internalize it. And model monitoring systems continuously compute the mathematical distance between these statistical distributions. When that statistical distance gets too large, crossing a threshold that you, the engineer, defined, an alert fires.
Okay, that sounds really great in theory, but let's look at the operational economics of actually doing this in the real world. Because watching every single data point flow through a system to check for drift must be incredibly taxing on the servers. There is a case study here in the material about forecasting product sales based on historical transactional data.
Right, a very high volume scenario.
Yeah, you are a massive retailer. You are anticipating changes in user buying patterns. Maybe the seasons are changing, so you know you absolutely need to monitor for prediction drift. But because of your massive scale, you are receiving an enormous volume of prediction requests, like millions of requests a day hitting your model.
High throughput, the fire hose is just fully open.
Right. And you want to use Vertex AI Model Monitoring to detect this drift, but you have a strict budget from your boss. You want to minimize the cloud computing cost. Because computing complex statistical distributions on millions of individual data points every single hour is going to incur a massive, massive server bill.
It will bankrupt the project in a week.
So the solution provided by the engineers in the guidelines is to use the relevant features for monitoring, but to set a configuration value called the prediction sampling rate. And you set that rate closer to 0 than 1.
Yes.
Now, I have to stop you and push back here. Because if I set my sampling rate closer to 0, let's say 0.01, which is 1%, that means I am intentionally, knowingly ignoring 99% of my live prediction requests. I am literally throwing them in the trash. Aren't we essentially flying blind? If I only look at 1% of the traffic, how on earth is that safe? It sounds incredibly negligent.
It absolutely feels counterproductive. I totally get that, especially to a traditional software engineer who is used to logging every single individual error. But machine learning monitoring doesn't rely on catching individual isolated errors. It relies on macro-level statistics. It relies on the law of large numbers.
Walk me through the math of that. Make me feel safe about ignoring 99% of my data.
Okay. If you have a low-volume model, say a model approving 50 multi-million-dollar corporate loans a week, you absolutely must monitor every single request, a sampling rate of 1.0, because every single data point deeply matters. But if you have an enormous volume of traffic, 1 million requests a day, you don't need to examine every single drop of water to know if the temperature of the entire ocean is changing.
So a small random sample is statistically valid to represent the whole ocean.
Exactly. If you randomly sample just 1% or even 0.1% of 1 million daily requests, you are still collecting 1,000 data points a day. Mathematically speaking, a randomly selected 1,000 data points is a highly robust, statistically significant sample size to compute the true overall distribution of those features. If a viral trend starts or user behavior fundamentally shifts, that shift will absolutely be reflected in the 1% sample.
You will still catch the drift.
You will catch the drift with 99% accuracy, but your cloud monitoring compute costs will be a tiny, tiny fraction of what they would be if you logged and analyzed all 1 million requests. It's the pragmatic reality of professional engineering. You always have to balance statistical risk with your financial budget.
Okay, I buy that. We are sampling efficiently, we are saving the company money, and we have set up our alarms for skew and drift. But what happens when the alarm actually rings? Like if an engineer just gets an email every time there's a drift, and then they have to manually pull the new data, manually spin up a training pipeline, manually validate the new model, and manually deploy it, they're going to spend their entire lives just fixing broken models.
Which is why the holy grail of machine learning operations, or MLOps as they call it, is the self-healing system.
Yes. The documentation outlines a really beautiful architecture for automating the fix. Let's trace this pipeline, because it's a perfect example of modern cloud architecture. The scenario here is a BigQuery ML model predicting customer churn, which is basically predicting which users are about to cancel their subscription. It's a critical business model deployed to Vertex AI endpoints. You want to automate the retraining of this model using minimal additional code whenever feature values change, but you also want to minimize the number of times it's retrained to reduce costs.
Right, you don't want to just set a cron job to lazily retrain the model every single night at midnight.
Right.
Retraining a massive model on big data is very expensive. If the real-world data hasn't actually drifted, retraining is a total massive waste of money. You only want to spend the money to retrain when the world has actually shifted.
So how do we build the self-healing loop? Step 1. You create a Vertex AI model monitoring job configured to monitor for prediction drift. We just talked about that. It's sampling the traffic, watching the distributions. Step 2. You configure the alert monitoring to publish a message to a pub sub queue when an alert is actually detected.
Let's pause there for a second. The model monitor is basically the watchman in the tower. It sits there, looking at the 1% sample. Suddenly, it detects a significant drift in user behavior. The alarm fires. But it doesn't send an email to a human. It sends a digital message to PubSub.
Which is basically a highly reliable asynchronous digital mailroom in the cloud.
Yes, exactly. PubSub guarantees the message is delivered and securely held until someone, or in this case something, reads it.
Step 3. You use a cloud function to monitor that PubSub queue, and when a message arrives, the function automatically triggers the retraining process in BigQuery.
Exactly. Sitting on the other side of that digital mailroom is a cloud function. A cloud function is just a lightweight, serverless piece of code. It costs you absolutely nothing while it's sleeping. It only wakes up when a new message drops into the PubSub queue. The moment the drift alert message arrives, the cloud function wakes up, reads the alert, says, drift detected, and it fires off a command directly to BigQuery.
And BigQuery executes the SQL needed to pull the freshest, newest data and retrain the churn model.
Yes. And once the new model finishes training, it can be automatically validated and deployed to replace the old drifting one.
It's a fully automated, closed feedback loop. The AI watches the AI, and it literally heals itself. It's incredible. But as with literally all automation, humans can still find a way to mess it up, which leads to one of the most interesting, kind of funny warnings in the material: the ghost alert phenomenon.
Oh man, this is a classic, deeply frustrating engineering headache.
So here's the scenario. You receive a training serving skew alert from a monitoring job running in production. The watchman saw a skew. Okay, the system works. You get the alert, you look at the data, you agree that the real world has skewed away from the training data. So you step in, you manually retrain the model with the more recent accurate training data, you validate it, and you deploy the newly fixed model back to the endpoint. The fire is out. But 20 minutes later, you are still receiving the exact same skew alert from the monitor. What just happened?
Why did the alarm keep ringing after the fire was put out?
The answer is brilliantly simple and honestly a little embarrassing. You forgot to update the model monitoring job to use the more recent training data as its new baseline.
This is such a profound lesson in how we interact with these automated systems. Think back to our definition of skew. The baseline for skew is the training data. When the engineer retrained the model on the fresh data, they fixed the model. The model itself is now accurate, but they forgot to update the reference manual for the watchman.
The monitor was still holding the old 2018 textbook.
Exactly. The monitoring job was still comparing the live, fresh traffic to the old, outdated training data from version 1 of the model instead of the new training data from version 2. Of course, it kept firing an alert.
Yeah.
It saw the new data and screamed, "This doesn't match the 2018 data."
It's a perfect example of human error in automated systems. The system did exactly what it was mathematically told to do.
Yeah.
It just had an outdated definition of what normal looked like. You have to update the baseline.
It proves that you can't just deploy monitoring and walk away. The monitoring infrastructure requires just as much lifecycle management and attention as the model itself.
Okay, so let's take a breath and look at where we are. We know how to explain the model's complex math using SHAP and XRAI. We know how to set up statistical monitors to watch that math as it interacts with reality. And we know how to automate the fixes. We have built an incredible, automated, highly accurate machine. But making sure a model works mathematically is really only half the battle. What if the math works perfectly? What if the monitor is completely quiet, no skew, no drift? The model is highly accurate, but the outcome that the model is generating is deeply, fundamentally ruining someone's life.
This is the hard pivot. We have to move from engineering capability to engineering ethics.
And this brings us to the third pillar, responsible AI. The guidelines lay down the law here. They start with Google's AI principles. Now, I'm not going to read this as a dry checklist, but they basically outline 7 core objectives. The AI must be socially beneficial. It must avoid creating or reinforcing unfair bias. It needs to be built for safety, accountable to people, respect privacy, maintain scientific excellence, and be restricted to uses that accord with these principles.
This is a very strong, comprehensive philosophical framework.
Yeah, but I have to be honest here. If I am a developer sitting at a keyboard staring at a command line, these principles sound great on a corporate poster in the break room, but they are incredibly high level. How does an engineer actually code fairness? How do you take a philosophical principle like avoid unfair bias and turn it into a Python script? Because Python doesn't just have an import fairness module you can download.
That is arguably the absolute hardest part of modern machine learning. is not just about having good intentions. It is about applying rigorous statistical methodology to ensure those intentions are actually mathematically reflected in the model's output. The documentation gives us some very concrete, practical examples of how engineers navigate unfair bias in the trenches.
Let's look at the first case study here. Targeted ads. You are an engineer developing a model to help your company create more targeted online advertising campaigns. You need to pull data from your warehouse to create the training data set. But you have a strict mandate from leadership. You explicitly want to avoid creating or reinforcing unfair bias across different demographic groups.
Now, the naive approach, the approach a lot of junior engineers take when they first face this problem, is what we call fairness through blindness.
Which means just removing demographic data entirely from the spreadsheet.
Right. They think, well, if I just delete the columns for race, gender, and age, then the model can't possibly be biased because it literally doesn't know who anyone is.
It feels intuitively fair. Justice is blind, right?
But the engineering guidelines completely unequivocally reject that approach. It's a massive fallacy. To actually avoid bias here, you must take two specific actions that are the exact opposite of blindness. First, you must explicitly include a comprehensive set of demographic features in the data. Second, you must collect a stratified sample of production traffic to build the training data set.
Okay, let's really unpack this. Why does blindness fail? Why must we intentionally include the demographic data?
Because you cannot fix what you cannot measure. If you delete the demographic columns, you have absolutely no mathematical way of auditing the model after it's trained. How do you know if your model is disproportionately showing high-paying job ads only to men? You wouldn't know because you deleted the gender column. By explicitly including comprehensive demographic features, you can evaluate the model's performance across different cohorts later. You can measure the error rates for Group A versus Group B and actually ensure equitable treatment.
You have to shine a light on the demographics to prove the model isn't secretly exploiting them. Okay, what about the second part? A stratified sample instead of a simple random sample. What is a stratified sample and why is it so crucial?
Think about what happens if you take a truly random sample of your production traffic. The majority groups will naturally dominate that data set, simply by sheer volume of numbers. If a specific minority group only makes up 2% of your total user base, a random sample of 100,000 clicks will only contain about 2,000 clicks from that group.
Which, I mean, sounds proportional.
It is proportional to the overall traffic, but it is mathematically insufficient for a deep learning model to learn from. The model will spend 98% of its time optimizing its math to perfectly understand the majority group, and it will essentially ignore the minority group because there just aren't enough examples to learn their specific patterns. This leads to high error rates and incredibly poor performance for that specific group, which is a structural mathematical form of algorithmic bias.
It's a statistical blind spot. The model just ignores them because they aren't worth the compute cycles to figure out.
Exactly. A stratified sample fixes this entirely. It forces the dataset to guarantee a sufficient representative number of examples from all demographic groups, regardless of their overall proportion in the total traffic. It might intentionally oversample the minority group, basically duplicating their data, ensuring the model has enough raw data to learn how to serve them accurately and fairly. You have to intentionally, actively engineer the data to force the model to pay attention to everyone equally.
That is fascinating. You have to actively manipulate the dataset to create fairness. Let's look at an even trickier example, the telecom unpaid bills scenario.
Oh, this one highlights the most insidious problem in all of machine learning: proxy variables.
Here's the scenario. You work for a telecommunications company. You are building a model to predict which customers might fail to pay their phone bill next month. But the purpose is positive. It's to proactively offer at-risk customers assistance, like service discounts or deadline extensions. The data you have includes customer ID, age, salary, sex, average bill value, number of phone calls last month, and average duration of phone calls last month. Your mandate is to investigate and mitigate potential bias against disadvantaged groups while preserving accuracy.
The massive risk here is that sensitive features, like age or sex, might be secretly driving the predictions in ways that are socially unacceptable or frankly legally non-compliant, even if the pure math finds them highly predictive of missing a payment.
So, do we just drop age and sex from the table before training? We just learned that blindness doesn't work for auditing, but maybe we shouldn't train on it.
If you just drop the sensitive columns before training, you run face first into the proxy problem. Let's say you drop age. But what if average duration of phone calls is highly correlated with age? What if older customers simply tend to have much longer phone calls than younger customers who prefer texting?
Oh, if the model is trying to predict who won't pay and it inherently wants to use age because it's mathematically useful, but age is missing, it will just look for the next best thing.
Exactly. The model will use duration of calls as a proxy to silently figure out the customer's age behind the scenes. It will still make biased decisions based on age, but now it will be hidden behind a completely innocent-looking variable like call duration.
It is literally laundering the bias through a proxy variable. That is terrifying.
It happens constantly, all the time. So the proper engineering solution provided in the guidelines is a strict three-step process. First, you train a BigQuery ML model with all features included, even the sensitive ones like age and sex.
Hold on, wait. You're telling me we explicitly feed the sensitive data into the model to train it? We intentionally let it build its inherently biased logic first. Doesn't that feel incredibly dangerous, like letting a biased system loose just to catch it in the act?
You aren't letting it loose in production. You're letting it loose in the lab. If you don't let the model clearly see the sensitive data, it will find a proxy. By giving it the sensitive data, you force it to put its bias right out in the open where you can actually see it.
Okay, I see. Keep your enemies close. What is step 2?
Step 2. Step 2, you use the global explainability tools we talked about way back in the first pillar to calculate the global attribution values for each feature across the entire model. You look at the menu.
You see exactly how much weight the model gave to age versus salary.
Exactly. And step 3, if the feature importance value for any of the sensitive features exceeds a predefined, socially acceptable threshold, then you intervene. You discard that model entirely, and you start analyzing the correlations to find the proxies, and you retrain. You are using the explainability tools to mathematically audit the model's reliance on sensitive traits. You don't guess about bias, you mathematically measure it.
This is such a clear example of why these pillars aren't just isolated silos. The first pillar, explainability, is an absolute prerequisite for the third pillar, responsibility. You cannot enforce ethics on a black box. You have to rip the box open first.
They are a single, interconnected, mandatory framework for governance.
And speaking of governance, the principles don't just tell us how to mitigate bias. They draw absolute red lines on what not to do. The guidelines list 4 areas of application that should not be pursued under any circumstances. Technology is likely to cause overall harm. Technology is primarily intended to cause injury, surveillance violating internationally accepted norms, and purposes contravening international law and human rights.
These red lines are vital. You really have to remember a fundamental truth about AI. AI scales intent.
Say more about that. What do you mean it scales intent?
Well, in the physical world, a human with bad intentions can only do so much damage, right? Their harm is localized by physics and time. But if you encode bad intentions, or even just reckless disregard for human rights, into an AI model and deploy it to a massive cloud infrastructure.
A bad AI can harm millions of people instantly. It operates at digital speed and global scale. Like, if you build a biased facial recognition system for surveillance, it doesn't just misidentify one person on a street corner, it misidentifies tens of thousands of people across a whole city simultaneously.
Exactly. The potential for automated scalable harm is just unprecedented in human history, which is why these do not pursue boundaries have to be absolute. Accuracy isn't enough. If your model's math is pristine but it relies on mass surveillance, the project is a total failure. You aren't just optimizing for speed or profit. You are forced to optimize for human rights.
So we have our ethical compass, we have our monitoring alarms, we have our explainability tools. But all of this, the principles, the monitoring pipelines, the careful debiasing, is completely, totally useless if any random person on the internet or any disgruntled employee can just log into your cloud environment and change the code, steal the data, or just turn off the monitors. We need walls. We need locked doors.
Which brings us to the final foundational pillar, IAM, Identity and Access Management.
The architecture of security. The guidelines start with the fundamentals of resource management in Google Cloud. It outlines a really strict inheritance model. It goes in this specific order: organization, then folders, then projects, and finally, resources.
This hierarchy is incredibly important for maintaining control over massive, sprawling enterprise systems. Without it, you just have total chaos.
I like to compare this to a massive corporate skyscraper. The organization node at the very top is the entire building itself. It's the front door security desk in the lobby. The organization-wide policies apply to everyone who enters the building, no matter what floor they are eventually going to.
And then inside the building, you have folders.
Right. Folders are like specific floors or wings of the building. You might have an HR folder, an R&D folder, a production folder. They group things together for security governance. Then, within a folder, you have projects.
Projects are the fundamental logical grouping in the cloud.
They are the individual locked offices on that floor. And inside those offices, you finally have the resources, the actual virtual machines, the cloud storage buckets holding the data, the deployed AI models. Those are the filing cabinets and computers sitting inside the locked office.
And the most important security concept here is strict inheritance. Policies flow downward, and they cannot be overridden by lower levels. If the organization at the top floor dictates a policy, say, no resource can ever have a public IP address facing the open internet, that policy flows downward instantly. It applies to every folder, every project, and every single resource beneath it. If a junior developer inside a specific project tries to make their database public, the system will just hard block them. You cannot override an organization-level restriction at the project level.
It's the ultimate trump card. The office worker cannot overrule the lobby security. So that is the structure of the building. But how do you actually determine who gets the keys to where offices? That is identity and access management.
The core philosophy of IAM is the principle of least privilege. You grant a user only the minimum exact necessary access required for them to do their specific job and nothing more. If a data scientist needs to read a database to train a model, you give them read access. You do not give them delete access, and you certainly don't give them owner access.
The text provides a very simple equation for how IAM works. Identity plus IAM role equals an IAM policy, which is then applied to a specific resource. So the identity is the who a user email, a Google group, or a service account. The IAM role is the what a collection of specific permissions, like storage object viewer, and you bind those together into a policy and apply it to a which the specific project or bucket.
It sounds super straightforward when you talk about humans. Bob gets read access to the HR folder. Simple. But in a modern machine learning environment, it gets incredibly complex very quickly, because it's not just humans who need identities anymore.
Let's look at a scenario that perfectly illustrates this. I call this the frustrated data scientist.
It's a scenario literally every cloud engineer has faced at least once.
You recently created a new Google Cloud project. You test that you can submit a Vertex AI pipeline job from your own local laptop using the Cloud Shell. It works perfectly. The pipeline runs, you clearly have the right access, but you want a more robust cloud-native setup, so you spin up a Vertex AI Workbench user-managed notebook instance. It's essentially a powerful Jupyter notebook running in the cloud. You write the exact same code, you hit run in the notebook, and boom, the job fails with a massive insufficient permissions error.
And the data scientist is sitting there pulling their hair out thinking, I have the permissions. I just ran this 5 minutes ago from my shell. I am the project owner.
Exactly. What is actually happening here? The solution provided is that you must ensure that the Vertex AI Workbench instance itself is assigned the Identity and Access Management Vertex AI user role.
This requires a profound shift in how we think about identity. When you run code on your laptop or in your personal cloud shell, the system is acting on behalf of your human identity. It checks your IAM and permissions. But when you spin up a Workbench notebook in the cloud, that notebook is a separate virtual machine. It is a discrete, independent entity.
It's basically a robot worker you hired.
Yes, and that machine needs its own identity badge, what we call a service account. When the code runs inside the notebook and tries to talk to Vertex AI pipelines to start a job, the cloud infrastructure doesn't look at you. It checks the notebook's permissions. If you didn't explicitly give the notebook's service account the key to the pipeline office, the door stays locked. Machines need identities to talk to other machines securely.
That is such a vital concept. The security perimeter isn't just drawn around the humans anymore. It's drawn around every single individual component of the architecture, which leads perfectly to our final and perhaps most critical scenario: securing sensitive data.
This is where the security pillar and the ethical responsibility pillar just smash into each other.
The scenario: you are analyzing customer data for a major healthcare organization. This data is stored in cloud storage. It contains massive amounts of personally identifiable information, or PII. Patient names, home addresses, phone numbers, maybe even social security numbers. Your data scientists desperately need to perform deep data exploration and pre-processing to build predictive health models.
But they absolutely cannot be allowed to see that raw PII. It violates every privacy principle we discussed, and more importantly, it aggressively violates federal regulations like IP pay. If a data scientist downloads a spreadsheet with raw patient names, the company is facing massive, ruinous fines.
So how do you balance the ethical mandate for privacy with the mathematical needs of your engineers? The data scientists need the data to find patterns. If you lock the data away completely behind IAM, they can't build the model.
The solution relies on a specific automated tool, the Cloud Data Loss Prevention, or DLP API. The strictly correct action is to use the Cloud DLP API to completely de-identify the PII before performing any data exploration and pre-processing.
I view the DLP API as sort of a digital bouncer standing at the door of the database. Before the data scientist is even allowed to open the file, the bouncer sweeps through the data and redacts or masks all the sensitive information.
Exactly. And it's highly intelligent. It uses machine learning itself to scan the text. It will find a string that looks like a name, say John Doe, and replace it with a cryptographic hash or a generic tag like person name 1. It will find a phone number and replace the first 6 digits with asterisks.
But it preserves the structure.
Yes, that is the absolute key. The underlying shape of the data, the medical history, the lab results, the billing codes, remains entirely intact. Person name 1 still has a history of high blood pressure. The data scientists can still analyze the correlations, they can still train the model on the patterns, but the human identity attached to that data is irrevocably stripped away. You protect the fundamental privacy of the patient while still enabling the mathematical insights of the AI.
It's a technological solution to an ethical mandate. It's just brilliant. Looking at all of this together, from the complex math of SHAP to the bouncers of DLP, I have to just marvel at the sheer overwhelming complexity of the modern machine learning engineer's journey. It used to be that you just needed to know the math. You just needed to know how to write the Python code to train the model, and you are a hero.
That was the easy part, but that was 10 years ago.
Now you have to write the code. Then you have to mathematically explain the code using cooperative game theory and Shapley values. Then you have to set up statistical monitors and fully automated pub-sub feedback loops to watch the code in production. Then you have to audit the code for societal bias, stratify your samples, and ensure ethical compliance. And finally, you have to lock the code down with an intricate web of strict inheritance, least privilege, and machine-machine service accounts.
It is a phenomenal evolution of the discipline. It has really moved from a quirky laboratory science to a rigorous, high-stakes industrial engineering practice.
And speaking of that journey, as we start to wrap this deep dive up, there is a piece of advice buried in these engineering guidelines that is aimed directly at you, the learner. After hundreds of pages of dense architecture, it simply says, enjoy the journey as much as the destination.
It can absolutely feel overwhelming when you look at it all at once, but the process of building these robust, safe systems is incredibly rewarding.
And they mention a specific practical resource for practicing all of this, the Google Cloud Arcade. It's an initiative to boost your cloud skills for no cost. You play hands-on games to earn digital badges, and you gain actual expertise that is usable immediately in these environments. It sounds like a fantastic way to actually get your hands dirty with Vertex AI, pub/sub, and IAM policies without having to set up your own complex, expensive environments from scratch.
I highly recommend it. Practical, hands-on application is honestly the only way to truly internalize these concepts. You have to accidentally lock yourself out with a bad IAM policy to understand why it matters. You have to build a monitoring pipeline and watch a ghost alert fire to truly understand the baseline.
So let's just quickly look back at the map of what we covered today. We started by demystifying the black box with explainable AI, learning how tools like SHAP and XRAI let us look over the model's shoulder and understand its logic pixel by pixel and feature by feature.
We then explored the reality of a shifting world with model monitoring, setting up the automated alarms for training serving skew and prediction drift, and understanding how to balance statistical sampling with hard cloud costs.
We tackled the ethical minefield of responsible AI, navigating the complexities of unfair bias, the necessity of stratified sampling, and the critical, often counterintuitive importance of measuring sensitive proxy variables instead of just ignoring them in the name of blindness.
And finally, we built the fortress with identity and access management, understanding resource hierarchies, and the crucial concept that machines, just like humans, require strict identities and the absolute principle of least privilege.
It is a massive amount of information, but it all connects to that one central overriding goal, trust. We are building systems that make decisions about human lives. We have to make AI that we can actually rely on. But before we go, I want to leave you with one final thought. The expert and I were looking at these automated systems earlier, and something really struck me.
Yes, it's a scenario that honestly keeps me up at night. We discussed the architecture where an AI model is deployed in production. We then configure a second system, a statistical monitor, to watch the first AI. When the monitor detects drift, It fires an automated alert to a pub/sub queue. That triggers a serverless cloud function. That function automatically commands BigQuery to retrain the model on new data. The new model is validated and automatically deployed. And all of this is secured by machine-to-machine IAM rules. No human ever clicks a button.
It is a fully closed autonomous loop. So here's the provocative thought for you to mull over as you go about your day. If this fully autonomous, self-healing, self-training loop eventually ingests a subtly skewed new data set from the real world and quietly trains a new version of the model that makes a deeply biased decision that harms a user who is actually responsible.
Is it the developer who wrote the original Python code 3 years ago? Is it the security architect who wrote the IAM policy that allowed the automation to execute? Or is it simply the mathematical reality of the new data itself? When the machine is entirely running the machine, where does accountability truly sit?
It's the ultimate muddy water. I'll leave you to think about that one. Thank you for joining us on this deep dive into the black box. Keep learning, keep questioning the systems around you, and we'll see you next time.